Right, in this example, we actually have a long set of questions to ask, or answer that is. All of them are about understanding what the stress-strain curves are, but this time we get three different materials that we can begin to compare and understand against each other. Right, so let's see how this goes. We've got, of course, answers are already provided for us, but let's try to respond without looking at those answers. Right, so number one, we've been asked, find the elastic modulus for material B. Given three materials A, B, and C, and we want the stiffness in the linear elastic region for that one. Right? So note that all three of these actually have straight line variations at the beginning. We just want to focus on B, and so that elastic modulus E delta sigma over our change in strain from two different points. Let's use 0, 0, and we'll use this yield point that's up here. So that would be 40 KSI over the strain value, and that strain value is 0.002 inches per inch. Right, so of course we could probably do that one in our head, but we'll do it on the calculator. 40 divided by 0.002, and that's going to be then 20,000 KSI, and that's usually the way people leave it, but it really to be proper would be per inch per inch. There we go. That was what we agree with what someone suggested was their answer to this at 20,000. Then we're asked to find the most ductile material. Now remember, ductility is the opposite of brittleness. Brittle, something breaks without hardly any warning that's going to happen, whereas ductility is the ability to deform before rupture, normally characterized by a large plastic region. One way to characterize it was with this large region between the strain fracture and the yield location. Now note that here, each one of the three materials, A, B, and C, all yield. They all have a sudden change in their stress-strain behavior at the same strain. So this is, for the most part, the yield strain, or it would look like it at some level. There's other things we'd like to know, but it's a reasonable interpretation that that would be the case. And there's a couple of things that might say, well, definitely B that's the yield point here for B. For A, it's probably about 60 KSI, right? Because it begins to curve over a little bit. C is a lot more ambiguous. There's a post-yielding stiffness. It's not flat. It has a lot of stiffness. So maybe this is elastic. We need to unload in here to really know where do we have the end of elastic behavior. Right? So this is maybe a little ambiguous, but no, it does look like something significant happens for all three at this strain value of 0.002. By the way, this drives me nuts that the person who originally created this did not give us the leading zero in front of those decimals. That's not proper. They did it because of clarity of the scale. And notice too that when they plotted this, there's a scale change. It's very common to break these because of sometimes many orders of magnitude. Here are 2 orders of magnitude that we're stretching the scale out over, just so we can zoom in on one portion, etc. Right? So note that without a doubt, B has the largest rupture strain. It's out here somewhere around 0.35-ish, and it's much larger than the rupture strain for A, a little bit larger than that for material C. I think the answer's got to be B, just based on strain. Now, if you want to base it upon energy, remember that's area under the stress-strain curve. In that case, this is not so clear because the total area out here in the plastic region that is talking about ductility for C might equal or exceed that for B, even though B goes out further to the right, but it's not as high. So you got to, sometimes these things are ambiguous, and you have to state clearly, well, what was the basis of your selection, right? And basis here was on strain. We had the largest fracture strain or rupture strain, let's call it fracture, minus the yield strain region. Right? Okay, so now the most brittle material turns out to be A by far and away. Here's our yield stress somewhere around here and yield strain. Here's our rupture strain. That's got the smallest both energy and strain region there. So clearly A on that one. The proportional limit for A, well, that looks to be fairly close to being right there at 60 KSI. It's the end of linear elastic behavior. That'd be PL, not the yield stress. For material B, then we have a very clearly marked and indicated yield stress, so that's going to be the 40 KSI. That's pretty straightforward. The yield stress of material C, if we use the 0.2% offset method, which would be something I probably would do with C, then if we do it that way, look what's going to happen. We're going to go out to 0.002 strain, or 0.2%, which would be here. And when we do that, if we call this then the yield strain for C, then its region between the fracture and the yielding is clearly much smaller than B, because we declared now that how to do this slightly differently for that one. And then the yield stress for C for that 0.2% method is going to be on the order of about 56, 57. It's a little hard to read there. Someone who first developed this, and maybe if we were really careful about getting this parallel, we probably would get right up to about 60. It has a lot to do with how carefully you draw this sloped line. So it's certainly in the region of 56 to 60 KSI, and on a test, I have to be a little bit more liberal in how I interpret what you do. You have to very clearly indicate how you're approaching this and what your intention is, and then I can say, okay, the process is appropriate and you have a reasonable number. Ultimate strength is the maximum stress that we see in the stress strain curve, and certainly with A, that's up here at 70 KSI, so I agree with that. The stiffest material is the one that has the largest slope in the linear elastic region. Again, that's clearly going to be A. In fact, in order, you'd say EA is greater than EB is greater than EC in this particular case. The most resilient material is the one that has the greatest amount of energy associated with the linear elastic region, so that doesn't have to be the greatest stiffness, but notice A has the greatest stiffness and the greatest proportional limit, so it's clearly going to be, the answer is going to be A. That area here would be our modulus of resilience. So modulus of resilience for A larger than the other two. It's a little hard to see, but I'm going to bet that with the way we looked at C, it's going to be next, and then that would make B have the least amount of resilience, all based upon all this area that's sitting out here for C. And then the toughest material is the one that has the total amount of energy, or area, really total amount of energy. This could be argumentative all the way up to rupture, whether it's really B or C. It's without doing all of the actual calculation, it's a little bit harder. You've got some area out here in C that would balance the difference between B and C. Yeah, that's a little bit tough but we got this extra area out here in B. So I think it's B, but it could be C. C is probably not too far off, at least by I.